Okay, so now that we have our model defined, we can start performing inferences. And to do that, of course, we will be performing the MCMC, a Markov chain Monte Carlo simulation, and let's do it. So at the beginning of this tutorial, we defined two vectors, a vector of moves and a vector of monitors. Up until now, we have been filling the vector of moves with different moves. Essentially, whenever we define the stochastic node, we define the move. But regarding the monitors, we haven't up until now defined any monitors. And what are monitors? So essentially, monitors will be outputting the states of the MCMC. Of course, we are visiting the posterior in different places, and we wanted to keep those places. And we have essentially two types of parameters here. Of course, the continuous parameters like the GC bias rate, the base composition, the exchangeabilities, but we also have the topologies and the branch lengths or the phylogenies to be kept. So in order to do that, we use these two functions here. So of course we are appending a monitor in both cases, but in these cases we are keeping track of the continuous parameters, and in this case we are keeping track of the phylogenies. Another thing that we probably wanted to output is some information for us to know what is happening while the MCMC is running, and this monitor here, this function mn screen, is just outputting something to my screen, and I'm telling Rebase to output me something after every 10th iterate. So let's do it. So first move for the continuous parameters, second move for the phylogenies or the sampled phylogenies, and finally a move for outputting something on my display. I wanted to see something happening while Rebase is running. And yeah, so once we set the monitors, we can then define a Markov chain Monte Carlo object, which I called POMO MCMC. So what does it need? First, the POMO model, of course, that we have previously defined, a vector of monitors, a vector of moves, and here I'm just telling how many runs do I want the MCMC to run or to start with, and this is 2 runs. So I just do that, and now that we have defined the MCMC, we can run the MCMC. For that, we just need to define the number of generations that we want it to run. 10,000 is probably not much, but let's give it a try. And yeah, so as you can see, I'm seeing something appearing on my screen, and this is some information about what is the iterate, the posterior value. We also have information about the likelihood and the elapsed time, and also the expected time to finish. So in my case, it will take around 22 minutes to finish. Of course, this will take differently depending on the computer, but the important thing is that you should see something like this happening on your terminal. Otherwise, there's probably something missing, so just go back and see what are the lines that are missing in your Reb script, because probably something is missing. But if everything is okay, you should start seeing something like this. And now let's wait for it to finish. Okay, so now that we have our MCMC done, so as you can see here, it's finished. Let's now summarize some parameters, and of course one of them is just to summarize the tree. In specific, we'll be estimating the maximum a posteriori tree. To do that, we first read all the sample trees, and this is exactly what I'm doing now. So it's done, and now I'm just calculating the maximum a posteriori tree based on the trace reading, and then I will be just saving the maximum a posteriori tree to the output folder. This is what I'm doing here. So let's do it, and it's done. So it is produced. I can now go there and read it. Okay, now that we have our maximum and posteriority tree estimated, let's have a look at it. And this is it. The first thing that we notice is that most of the posterior clade probabilities are quite low, specifically for these clades here, and this is because we are only using a toy example with 1000 sites. If we were to estimate this species tree, we would of course use genome-wide data, which typically has 1 million and even more sites, and of course we could have made these posterior clade probabilities more accurate. Another thing that is strange in this topology is that the gorillas are clustering together with chimps, and we would not actually expect that. We would expect the humans to be clustering together with chimps, which is not happening, but again we are just doing it an example with 1000 sites. Another thing that we of course wanted to look at is the convergence of the continuous parameters, and here I'm just showing you the tracer for this MCMC run, and of course we have a lot of branch lengths, all the branch lengths that we have estimated here, and this is gamma, so this is the GC bias rate, and as you can see the trace plot is not really something that we would like to have. It seems that it achieved convergence, but the mixing is not that good. We can still see this series of regions where the parameter seems to be sampled from the same value, and of course we would like to improve mixing, and of course we can do that by increasing the number of generations. But as you can see, the ESSS seems to be fine, and let's look at the marginal density and then the histogram. Okay, it's sort of fine, but of course this is showing that we need to run our MCMC for a little longer. This is the base composition, so we can see there's an over representation of A and T's, and this is of course the exchangeabilities, and the exchangeability for the rate AC, AT, AG. AT is a little bit lower than the other ones, but it seems pretty homogeneous actually. But yeah, that's it. So let's have a look at the trace plots. Okay, this is not very informative. Let's have a look at. So they seem to performing a little bit better than gamma, but yeah, looking at the GC bias rate, we would definitely have to run this MCMC for a little longer. Okay, so I left you some exercises at the end of this tutorial. The first one is to rescale the GC bias rate. So as I've told you, we have done inferences using POMO 3 and assuming a virtual population size of 3. And we have no information about the mutation rates, the GC bias rate on the real population, but we know the effective population size on the real population. And among great apes, the effective population sizes are estimated at about 10,000 individuals. So we can use these values to rescale the GC bias rate, and this is essentially what I'm asking you to do in the first exercise. In the second exercise, I'm asking you to draw the probabilistic graphical model for POMO 2, and just a hint, keep in mind that POMO 2 cannot be used to estimate selection. In exercise 3, I'm asking you to change the POMO 3 rep script in order to make inferences now with POMO 2. And an exercise 4, I'm just asking you to compare the mutation rates between POMO 2 and 3, because this is a common parameter between them, to see what are the main differences, because in POMO 2 we are not estimating the GC bias rate. So let's see what actually is the cause of missing the GC bias rate or the selection aspect of the model on the mutation rates, which are a common parameter to both models. And finally, I'm asking you to produce the maximal posteriority tree under POMO 2, and compare them. And just a hint here, have a closer look at the branch lengths because they might be different. So with that, I finished the tutorial. I hope you enjoy it, and if you have some questions, you can of course send me an email or contact me by other means. But yeah, so thank you very much, and bye bye.